Hey guys, I'm Jade. Today is my LeetCode review vlog on the 101st problem, Symmetric Tree. We are given the root of a binary tree. We have to check whether it is a mirror of itself. Let's examine one here to understand this problem easily. For each node, we have to check if the left subtree is a mirror image of its right subtree. First, let's see the root node of the left subtree of node 1 here is node 2, and the root node of the right subtree of node 1 is also 2. They are the same. Next, we have to check if the left child of the left subtree is the same as the right child of the right subtree. They are both the node 3. Finally, we have to check if the right child of the left subtree is the same as the left child of the right subtree. Yes, they are both node 4. So all the nodes in this binary tree have their corresponding mirrored node, and their values are the same. So we just return true. Then let's get started with the intuition to solve the problem. We can solve this problem by two approaches. The first is called recursive depth first search, and the second is called iterative breadth first search. And we'll start it by the recursive approach first. Next, let's get started with the code and intuition to solve the problem. The very first step, we have to check for the edge cases, which is we'll return if root is equal to null. If so, which means this is an empty tree. And we also have to create another helper method to help us check if the tree is symmetric. Let's call the new method is mirrored. And there are two input parameters. First is the root node of the left subtree, and the second input parameter is the root node of the right subtree. So it is root.left and root.right. Next, we have to implement the method called isMirror. Private boolean isMirror. And two parameters, tree node left and tree node right. And inside this method, we have to check if both nodes are null. If they are both null, which means they are mirror of each other. If left equals null and right node equals null too, we just return true. Next, we have to check if one node is null but another node is not null, so they are not mirrored of each other. So in this case, if left equals null or right equals null, we'll return false. And for the third case, we have to check if their corresponding values are the same. If they are not, we just return false. If left.value is not equal to right.value, we also return false. Finally, we have to check if their respective subtrees are mirrored. So we have to reuse the isMirrored method to do a recursive operation. Return isMirror. And the first parameter is left.left and right, because they are mirrored. And we also have to make sure their second subtrees are also mirrored is mirror of left.right and right.left. And that's all the code for the first recursive approach. Next, Let's analyze its time and space complexity. So the time complexity, it is big O of n, and n stands for the number of nodes in the tree as we just visit every node for only one time. And the space complexity, it is big O of h, and h stands for the height of the tree as the space is used for the recursion stack. And in the worst case, the height of the tree could be n if the tree is an unbalanced tree. But if the tree is a balanced tree, which means it's the base case, it could be log of n. So h is between n to log of n. And that's the first approach. Next, let's implement the second approach. Version 2. The second approach is called iterative breadth first search. We'll create an extra queue to perform a level order traversal. Then we'll compare nodes level by level. Then let's get started with our code of the second approach and very detailed annotations. The very first step, we also have to check the edge case. If the root is equal to null, we just return true. Next, we have to create a queue to prepare for our level order traversal in the following code. Queue of tree nodes. Let's call it queue equals new linked list. Next, we have to put the two root nodes of the subtrees into the queue. The code is queue.offer root.left and queue.offer of root.right. Next, we have to create a while loop to process all the nodes while the queue is not empty. While not symbol queue dot is empty. And inside the while loop, first we have to remove the two nodes from the front of the queue. Tree node of left equals queue.poll. We have to get those two nodes. And tree node right pointer equals queue.poll. Next, we have to check if both nodes are null. If so, we have to continue to the next pair of nodes. If left equals null and right node equals null too, then we'll continue the for loop. Next, we have to check if the one node is null but another node is not null. Then the tree is now symmetric. We just return false. If left equals null or right node equals null, we'll return false. And for the third case, we have to check if the values of the two nodes are different. If so, we also have to return false. If left.value is not equal to right.value, we also return false. Then we have to add the Trojan of the nodes to the queue to prepare for the subsequent iteration. And code is queue.offer of left.left and q.offer of right dot right, right dot right, and q.offer of left dot right, and the last state, q.offer of right dot left. And that's all of the code in set value. And out of the value, which means we passed all the check, the tree is symmetric, so we just return true. And then we have to analyze the time and space complexity. The time complexity, it is also big O of n, and n stands for the number of nodes in the tree, and we visit every node for only one time. But the space complexity is big O of n. This is because we create an extra queue to store nodes, and in the worst case, the queue could store half of the nodes at the last level of the tree, which is big O of n. Then let's submit code to check for the correctness of the first approach. Yes, our first approach got accepted. Then we can rename the name of the method to check for the second approach. Let's submit the second approach's code. And yes, our code for the second approach also got accepted. And this is the end of my LeetCode review blog on the symmetric tree problem. And I really recommend you guys to visit my online GitHub page here, which contains all the nodes for the top 150 LeetCode problems. And for each problem, you can see problem description, intuition, Java code with annotations, and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the nodes and code to build this online GitHub page here. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.